Okay, so hello everyone. Saturday morning, good morning. So, but we'll continue. Still some interesting things to discuss after what we have done yesterday. So here is a recap. So since it is recap, I wrote everything before you come. So what did we do yesterday? We established reasons for inflationary expansion or quasi-de expansion. And we established the framework with a quite well motivated paradigm with R square term. And we looked at two regimes. When the modified gravity term is dominated, we have inflation, quasi-de regime. And when the GR term dominates, we get particle production or reheating. And we solve the equations. Easiest way to solve the equations is take FLRW metric, flat background, and take the 0, 0 equation, and it can be written in the form of first order differential equation. And we wrote that, and we solved it by iterative method. Well, it was solved by Alexei Starobinsky, but we just repeated the steps more carefully. And I will give the references in the notes. So but iterative method is basically you start with a solution, zeroth order solution, get it, and then say there is a correction, there's a first order solution, and you get the first order correction, which is y1, and then you get a solution for the scale factor. We discussed in detail yesterday about how the scale factor gives near exponential growth of the universe. And if you compute the Hubble parameter, it looks like this, and H dot during inflation, it's almost constant and negative. It decreases, but do not forget that there are some more terms I just omitted here. Otherwise, you will not exit inflation. Exiting inflation is the most important thing. Otherwise, it's not at all a realistic model. In literature, you find a lot of frameworks of inflation called power law inflation, where people take A to be some T power P, P is some number. And yes, you get inflation with this kind of ansatz, but you do not have exit towards a regime like matter-dominated era. Where is it? You wrote the solution. Here in red. It's reheating. So we get temperature, so it's right. So it's important. Otherwise, these are just toy models with no convincing framework of how the reheating happens. Of course, everything is possible with math, but not physics. Yesterday, we had discussed the philosophy. Okay. Now, we studied perturbations, scalar, and the scalar perturbations can be written in terms of Bardeen potentials. I will not go through a lot, so I will finish this recap in 5 minutes, okay? Don't worry, it's again a repetition of something. But just to bring you to the context, because these are and we also look at some new points to extract. And well, today I have a bit of satisfaction because yesterday I did not write these equations due to lack of time. Now they are written, so at least I'm happy. So now we did look at the perturbations. Scalar perturbations, there are two, and remaining thrown away by gauging variance. And among these two, there is only one dynamical freedom. And how do you determine? You look at perturbed equations of motion and you get constraints. The constraints are 2, pi plus I equal to 0, delta R, which is the perturbation of which is scalar, is also proportional to psi. In this calculation, we assume R bar, the which is scalar, is nearly constant, and there will be slow roll corrections, but we neglect them. You can ask why. I told you corrections are very important, but here I am neglecting them. Don't worry, we will bring back those corrections in the final computation of observables. We will see how that emerges. So, but keep in mind that this R bar is just not de Sitter case, but there are slow roll corrections which we will bring back at the end. So, in the approximation, it's like this. It's art of approximations. That's only physicists can do. Mathematicians do not like approximations. I mean, hardcore mathematicians. So, so if we understand how to do approximations, how to get a result which is good enough, then we become better and better physicists. So I'm learning, okay? So I'm just telling you what I learned from others. So yeah, you get these two constraints and then write the second order action to look at what is the dynamical degree of freedom. And you write all possible perturbations, and these perturbations, after imposing this constraint, just reduce to very simple terms, which you combine everything and a field redefinition, and you bring it to this form. This is a special form, and this Vs is Mukhonow-Sasaki variable, and this contains the scale factor, the background scale factor, which is the expansion, right? The de Sitter expansion, and it contains the perturbation. So the information of gravity, the background gravity, exponential expansion, and the fluctuation are encoded in this definition of the variable. That's why you do not have square root of minus g here. Okay. So far, any questions? Yeah.
Yeah. But to say that you can have essentially reheating with think about coupling something else to the photon. Or you just take into account that you have like gradients which brings the compensate.
Yeah, you can write any kind of Lagrangians and get things you want. The point is to get a consistent picture. Okay, nothing stops you to add a lot of terms to the Lagrangian and get it done, but those reheating mechanisms are not efficient. The first of all, you get a parameter p here. From where the p comes from? You see, in the Starobinsky inflation, for example, there is Ts, which is the end of inflation. It is kind of it depends on the mass m, which is the scalar on mass. So everything that comes from the physics that comes here. Everything is really depending on physics coming from the scalar on new degree of freedom. So if you add a parameter, how do you link to that? Okay, you can write a potential and say some potential as a power law, but those kind of potentials are not useful at all for any kind of UV completion, any kind of principles. We need to have a theoretical principles to start a model. If we do not have a principle, why not? Cannot be a motivation, at least from old school thoughts. So I will come back to that again, this possibility, because this possibility is what triggered the alternative models of inflation, and I will give some logic to why alternative models of inflation, why people have thought about it, and what are the problems associated with it and advantages. But we will come back to that. So it's not uh, the main topic, but I will maybe in the second part of the lecture. So coming back to this, look at this equation very carefully. As I explained, you have the background and perturbation, everything encoded in this variable. Let's think of like this. And yesterday we tried to understand how, okay, let me, this is a special box operator. Let me call it as some box tau. So I did not define it because this already absorbs the scale factor. So this action Vs minus d tau square plus di square. Because as I already said, this is special box operator. So let me define it, okay? So plus 2 by tau square, yes. Okay. Yesterday we discussed that this is where we stopped because this looks like a time dependent mass with a mass square negative. And we ended up saying this looks like an inverse harmonic oscillator. So to understand this, let us try starting with some scalar field in de Sitter background. So let me try it Lagrangian. Let's stop here and we go to some toy exercise. Then we will come back here and see how to deal with this. Let's take a Lagrangian, some scalar field, square root of minus g, d4x, phi, box phi. And in the flat orbital background, so you have square root of minus g. So we are taking in de Sitter case. In de Sitter, scale factor is exponential of ht. And in conformal time, you get, which is nothing but, okay? And so in conformal time, scale factor is written as this. By the way, none of you asked yesterday, so I was writing in some of the steps this curly h. Curly h is Hubble parameter in conformal time. So I hope it was clear to you, maybe in case for you to just notice. And here when I write h, it is the Hubble parameter, okay? Now you write a power 4 d4x and write the box operator in conformal time. It is 1 over a square d tau square minus 2h d tau plus di square phi, like this. So a square cancels, you have a square. Now, if you define some phi tilde, which is a times phi, and you make a substitution here, phi equal to phi tilde over a. This action, by the way, it's not too, okay? Yeah. This action will become d4x. Let me write explicitly d tau d3x. By the way, this should be a half factor, right? Overall. So phi tilde minus d tau square plus di square plus 2 by tau square. It looks similar to that, right? But here, what did we do here? Take a de Sitter background and take a scalar field in that background. It's like how you take Minkowski, you take a scalar field in that Minkowski background. We just did that to understand what's going on in describing fields in curved spacetime. And when you write like this, so this scalar field phi is in the curved background. It's the square root of minus g. Okay, what is the curved background? D square, a square. Well, here our curved background is de Sitter. So here we place this scalar field. Now we did a redefinition here in terms of phi tilde new scalar field where we absorb the scale factor. When we absorb the scale factor, remember, you see we started with a massless scalar field in a curved background. Then we rescaled it with the scale factor. What did we get? We get phi tilde in the background. If it is not there, it is Minkowski. Okay, so that means it's in a background like in Minkowski with a time dependent mass. This is the effect. This is the transfer of effect of de Sitter to a mass term that comes from a redefinition. So this field phi tilde is living in the space time like this phi tilde. This is where phi tilde is, but with a mass square minus 2 by tau square. Remember, we are following a signature, metric signature, minus plus plus plus. The Klein-Gordon field Lagrangian is box minus m square. Okay, minus m square. Because it comes with a plus sign, it's a negative mass square term. It looks like a tachyon to you, but it's not tachyon. There's a lot of physics involved. Why? The role of mass square negative is very important. This is the reason why quantum fluctuations evolved to become classical during inflation. If it is not like this, then the situation will be different. But this exercise tells you, I mean, forget about, this is all inflationary framework, right? This we just started with a scalar field. So that means any scalar field, massless field, you rescale it and you write it in a way like in a flat background, but you transfer the effect of gravity to a mass term. And somehow gravity is telling you that you get inverse harmonic oscillators. Again, you may be confused why I'm talking about harmonic oscillators. Let me remind you how you go from classical mechanics to classical field theory. In classical mechanics, you start with particles m like half dx dot by dt square. Sorry. This is basically the standard harmonic oscillator, like some particle, right? But when we go to classical field, we collect infinite set of harmonic oscillators coupled. And this coupled is exactly because you put the lot of particles in a lattice in some distance and take the distance limit to 0. And that's how you get this gradient term. Okay. And indeed, this is a Lagrangian structure, which is infinite collection of coupled oscillators with negative mass square. I hope that's clear to you. Any questions? Okay.
You mentioned that quantum fluctuations become evolved to classical theories.
We will do that. We will understand that. So I haven't done the quantization yet. What is quantization? Quantization when we promote the field to operators. I did not put that hats anywhere so far, but I'm just giving I will speak about it. Okay. Now, another observation. Now let's come back to, I think that description is clear. Now we come back to fluctuations around the inflationary background. They come to the same form, but there is a huge difference here. Here, in this case, we assume a de Sitter and we put some scalar field on the top of de Sitter. But here, these are the metric fluctuations around the background. Okay, that means we are considering the back reaction. We are computing correction to inflationary background, those corrections which are some homogeneities and anisotropies. So you see the metric is corrected here, and we compute the Barton potentials, which will give a geometry whose it is exactly, well, with a lot of transfer functions that CMB is representing us. All the temperature fluctuations in the CMB are sourced by these fluctuations, sourced by presence of scalaron. Okay, question here. So I was saying there is another degrees of freedom, it is scalaron, and you should think it as a field, a new degree of freedom of gravity, not as a particle. Indeed, this is a new field. It looks like some massless field. Where is the, I said there is scalaron, right? So the mass should appear here. It doesn't appear because during inflation, it is a field. And towards the end of inflation, the same field behaves like a particle. That is the whole process of scalaron. And then when it behaves like a particle, it's a heavy field, oscillate, and decays into all the degrees of freedom it is coupled to. Okay, where are all the degrees of freedom it is coupled to? We will come back to that. We can add the standard model there, and we can clearly see that during inflation, all the couplings to standard model are suppressed because the universe is completely dominated by the field. Only when this field come down to the energy scales, it feels the interactions with the ultralight particles, and then it decays, which will lead us from the scalaron matter dominated era to radiation dominated. And radiation domination is a bunch of photons and baryons. Then the universe cools down, and then matter starts to form. The role of dark matter is important. So that's how the whole universe evolves. It seems that we have completely understood, at least, although there are a lot of uncertainties in saying what is CDM, what is lambda. Apart from that, if you assume that, we kind of completely understand. So this is new physics. So I hope that part is clear. Now, in the next half an hour, we try to quantize it. Before we quantize this, let's try to quantize this, because it will be helpful for us to understand what's going on there. It's kind of identical thing, just written a toy model. And then whatever the solution you get for phi tilde, it will be valid for Vs. Yeah. Yeah, that's true. That's true. That's true. Because that's your curvature is dominant. So your mass is negligible. So, yeah. And because when you come to this scale, gravity is subdominant, and this is the heavy field, and this field will decay into ultralight particles. Yeah, you're right. So, okay.
It's larger than x squared.
Yes.
So what up is that with time h becomes smaller.
Yes.
So the curvature becomes smaller.
Yes.
Yeah.
Yeah. And when I think no one asked the question, maybe you could ask the question, what happens? There is a transition. During the transition, you can have curvature scale same as the mass scales, right? So that's where, I mean, it's a very fast transition, and that is something still fully needs to be studied. But in general, in that regime, that's where the particle production happens. But again, this is all in Jordan frame. This is all just gravity. Okay, in the Einstein frame, things would be different. So we have slow roll and we have the inflaton potential, so that there the picture is different. But we will go to the Einstein frame hopefully before the coffee break. Okay, now let's look at the field equations of this, and it is nice to understand in the momentum space. Why do we look at the momentum space? Suppose, let's say, this is the field we want to quantize. Okay. How do we quantize? We promote this field to an operator and just write the Fourier transform and A phi tilde K A dagger phi tilde K star. This is 3 vectors. This is just for the transform, and this phi k is a function of tau. Now, what is phi k? Phi k satisfies this equation. This is the famous Mukhanov-Sasaki equation, which you keep hearing in all the cosmology textbooks and papers. So everywhere it comes. So now, what do we understand from this equation before you attempt to solve it? Okay. Remember the tau is -1 over AH. Remember, again, we assumed h greater than 0, the arrow of time to be -infinity to infinity. That means tau less than 0. Even though our metric is completely independent of whether tau is positive or negative. Okay? We make this assumption. Let me just relate. Yesterday you heard Francisco explaining you Hawking radiation and stuff, and then there's a Penrose diagram, and only one region is picked because that's the region describes the black hole formed by collapse, although you have some parallel regions. It is similar to that. You choose a sign of tau because that corresponds to expansion in this choice of arrow of time. So you fix arrow of time, and then you pick this as a choice. Now, because this is this one, now if you substitute it here, actually it is this term is k square minus 2 by 2 a square h square, right? I'm just writing this term. Now let's ask a regime when your co-moving wave number much greater than 2a square h square. What does it mean? I already told you in this coordinate system, you have a particle horizon. Yesterday I used the word horizon, but to be precise, it is particle horizon. In this expanding universe, you have a horizon called particle horizon because the distance to which you can see at that moment of time. And so like it's a 3-dimensional space, and you see RH is a distance, and this particle horizon shrinks during inflation. Because scale factor is growing, h is constant. So the idea is basically, as I explained to you yesterday, I hope I explained you this. If you look at the CMB at present, any events separated by more than 2 degrees are causally disconnected now. Okay, so but still, if you look at correlations, temperature correlations, any 2 degrees, in less than 2 degrees, everywhere in the CMB sky, you get the scale invariant power spectrum, and you get the same structures, and the universe is statistically homogeneous and isotropic. So, idea of, well, we started with understanding that let's start the universe close to a symmetry, which is de Sitter space. But this idea translates to actually solving a problem called the horizon problem, because during inflation, so when the start of inflation, the whole universe, all the scales that are relevant for the CMB are inside a horizon or in causal contact. And then your particle horizon shrinks, then things go out of causal contact. Because they are in the causal contact in the beginning, in an equilibrium state, that means you can explain why the universe is statistically homogeneous and isotropic. Okay. I'm going slow, but please, if you're bored, say, Sravan, speed it up. Come on. Okay, please. Okay. Now, if you have a scale, for example, let's say you have some wave here with a wavelength lambda. That means wave number k. And if lambda is much less than this particle horizon, is deep inside the horizon, it doesn't feel that boundary. It doesn't feel much the effects of gravity. In principle, that is exactly this regime. If you can neglect this at some point, that means it looks like exactly some field living in the completely flat background. But then it starts to feel gravity when your particle horizon shrinks. And then, because this is changing with time, and at some point, your K will become equal to AH. And that's what you call horizon exit. Okay? Because your universe is changing with time. So that means this is a very important limit. For us, this tells us how to quantize the field. So let's write the solution of this. Phi tilde k, it has two solutions. Okay, it has two solutions, and there are arbitrary coefficients. You don't know how to fix them in principle, right? They are free coefficients, they are free constants. But remember that, yes. So these solutions determine what is the vacuum you choose. Okay. How do you choose A and B? You are doing quantization, right? How do we do quantization? First, we promote two operators, and then we impose uncertainty relation. Phi tilde and its conjugate momenta to IH bar. I drop H bar at some point, but just for you to remember, we are doing quantization here. And if you impose this condition, this actually kind of relates to the Wronskian in terms of the mode functions. One. Well, let me choose some coefficient here, square root of 2k. Just for convenience, because then only this is 1. And this gives you modulus of a square minus modulus of b square equal to 1. And surely you solve this equation and you get cosine hyperbolic alpha bk sine hyperbolic alpha. For any alpha, you can satisfy this condition. But then you still have a free parameter. You started with a solution which has two unknowns, A and B. Then impose the quantization condition. You get a relation. But then you still left with a parameter. Here we impose physics. Okay, well, this is all physics, right? Yeah, but here we are just playing with operators and commutators. So in the language of quantum mechanics, this is set up and compute job. Now we put logic. So remember this one. In this limit, by the way, it's k square. No, none of you corrected it. So anyway, I'm happy that I corrected it. So Okay, k square. In this limit, it is Minkowski. In the Minkowski limit, you would want your vacuum to describe like Minkowski vacuum, because in the sub-horizon limit, in the short distance scales, you don't see the much the curvature of spacetime. This quantum field is unaware about it. Or let's put it so I'm talking about phi tilde, right? This phi tilde, in the phi tilde language, actually this mass term, the time dependent mass term, is negligible. Okay, let's put it, let's see it this way as well. So this phi tilde has some kinetic term and a time dependent mass which is negative, right? So think of it like a some harmonic oscillator which has huge damping. It damps continuously. Okay, so yeah, now in this limit, because you impose a condition that you have to match with Minkowski vacuum, this tells you that you should choose alpha equal to 0. So if alpha is non-zero, it is in general called the alpha vacuum, and alpha equal to 0 is a choice called the Bunch-Davies vacuum. In general, that's the situation. But in the context of inflation, we do not quantize all the modes. We are quantizing only in those modes during inflation. There are only particular scales relevant during inflation. So in the context of inflation, only in this particular set of modes, you call this vacuum as adiabatic vacuum. It is most precise definition in the context of inflation. But in general, if you try to quantize a field in a digital background, alpha equal to 0 is called the Bunch-Davies vacuum. This is basically kind of investigated in 70s, so this is well-known thing. Any question? Adiabatic vacuum. It is approximately true, and also it is only for particular set of scales. You do not want to worry about, for example, there is this, you can say, I want to look at a fluctuation which has Planckian energy. You do not look at Planckian energy fluctuations during inflation. But Bunch-Davies vacuum, in general, mean all k, all infinite k. Although in the textbooks and later research, people use it, Bunch-Davies vacuum, but it is only mathematically true. Physically, it has to be called adiabatic vacuum. Clear? Cool. Once we have this, what do we compute? I think this can be arranged. Oh, maybe I would like to keep that, but anyway, right again. So, yeah, but well, I choose x. So, but yeah, in principle, delta direct x minus y. Yeah. So now your phi tilde looks exactly with some integral a exponential of minus I k tau 1 minus I by k tau exponential of I k bar dot x bar plus a dagger just the conjugate of this. Let me call it as phi k tilde star. Okay. Now what you want to compute is correlations. If you write this correlation and just use the Fourier transform and everything, you get basically uh, well, I integrated the theta and phi. Basically, you write it in angular coordinates, and then you get integrate theta and phi, and then you get kind of 4 pi factor, and it cancels. So these are basically, this is standard Fourier transform. So just to speed it up, I'm skipping this step. This is well known. Okay, phi tilde, yeah, is the same. So we here C is basically modulus of x1 and x2. So you're looking at a correlation of the field at different positions, x1 and x2. Now, these two parts together is called the power spectrum because it's function of k, and this is power spectrum of the field phi, and it is k cube by 2 pi square pi pi tilde, right? So far so good. But pi tilde is not the field you want to know, because remember we started with a field in curved space-time which is phi. Okay, so this is just a trick. We replace in terms of phi tilde to impose to implement the framework of quantization, because we only know how to quantize harmonic oscillators. So that's just a trick, but still we get some description of quantum field in curved space-time. And indeed, if you want to get a correlation of the field phi, by the way, this is a vacuum, Bunch-Davies vacuum. Well, here we are talking about exact de Sitter, but in the inflation, it's adiabatic vacuum. And this is nothing but this whole thing divided by a square, because you remember phi tilde is phi by a, or the opposite. What did we do? Phi is phi tilde by a. If you want the correlation for the phi, and you need to divide by a square. And this gives you the spectrum for field phi. It is k cube by 2 pi square pi tilde square 1 over a square. Now, okay, once you do this rescaling, remember that we imposed a commutation relation. By the way, this is for phi tilde, okay? This commutation relation for the phi tilde field. Now you write the commutation relation for the phi field, you get the scale factor divided by scale factor square. So what is happening, as the universe expands, the commutator vanishes. When the commutator vanishes, that's the classical limit. Does that answer your question?
Yes, but maybe I'll have to think about it.
Okay. So if you write in terms of the original field, then you get a scale factor divided by a square. And as the universe expands, this term becomes smaller and smaller. So when the commutator vanishes, you get classical limit, because in the classical theory, the field and the conjugate momenta commute. In the quantum theory, they do not commute because of uncertainty relation. So as the universe expands, you get the classical behavior of the field phi. And of course, it is still an open problem how to understand this transition from quantum to classical. It is an open area of research. All of you welcome to explore. There are a lot of fundamental questions which people do not understand. And people want to test quantumness of more quantumness of fluctuations. In the CMB, for example, there are questions related to entanglement. Can there be signatures of entanglement in the CMB and all? So all of these questions exist. So, by the way, right?
Phi not phi.
This one, but I divided by a square.
Started with phi tilde squared, so it's phi squared over a squared.
I'm talking about P phi. P phi is power spectrum of phi tilde divided by a square.
Ah, okay.
Yeah.
Okay, so the whole thing.
Yeah.
Same expression.
Yeah, exactly. That's it. Now, this is the one you want to compute because this is the field living in curved spacetime. I think let's erase this. So P phi is k cube by 2 pi square and phi k tilde whole square, and then basically we choose the Bunch-Davies vacuum alpha equal to 0, and you know phi k tilde, and just square it, you get 1 plus tau square k square tau square 1 over a square. Now, well, there is something is missing here. Remember these 2k factors. There is 2k. Is there anything missing here? Looks like no. Okay, so what you get, k cube cancel. It is 1 over 4 pi square, and tau square a square is inverse of h square. You get h square, and then you still get something tau k square, which is basically tau is 1 over ah. As the universe expands, tau goes towards 0, and then tau square. In the limit, tau goes to 0. This term goes to 0, then you are left with this term. Okay, cool. Now, this is what represents the correlation of phi field, and it is represented by this, like h by 2 pi. So that means averagely a fluctuation has some amplitude of h by 2 pi, and this is mostly known as the de Sitter amplitude. So you see, also it's also because you see you are placing a scalar field in a curved spacetime, and the curved spacetime here is de Sitter, and de Sitter is characterized by Hubble parameter square, and each fluctuation it carries some amplitude of h by 2 pi. It's also related to the temperature of de Sitter, and which is more formal aspects of understanding de Sitter space. But so all the physics behind all these formal aspects of de Sitter space is basically this calculation. Any questions? Clear? Excellent. So, given this is clear, we come back to our business of inflationary quantum fluctuations. Because we have a Mukhanov-Sasaki variable here, which tell us about the metric fluctuations. But at the end of the day, what you really want to know, the correlations related to metric fluctuations. Okay? That means, well, this is again a field which is redefined. It contains a scale factor, but also it contains some information related to what is the source of these fluctuations. It is F0. F0 term is related to scalar on degree of freedom, and it contains a lot of information than that exercise of toy model. But that is useful for us to really get answers here. If you repeat the procedure, you want to get correlation function for psi and psi. That is the Bardeen potential. That means this gives you the standard power spectrum, which is sine kr by r, k zeta by zeta, k zeta, dk by k, and some power spectrum associated with this p psi. And p psi is 1 over a square root of 24 f0 r bar p vs. So because you compute the modes for vs and you repeat the same procedure and you get a power spectrum for vs similar to the phi tilde field, and there is a square factor. This all gives you 1 over 16 pi square 3 f0 r bar h square in the limit tau goes to 0. But in the textbooks and the lecture, a lot of lecture notes, you hear that people evaluate the correlations at the horizon exit. Horizon exit is the moment when k roughly of the order of ah. That means your wavelength meets the particle horizon. That's where gravity meets quantum mechanics. That's where quantum effects are important. That's why we are doing all these things. Anyway, so what people do is evaluate the power spectrum at k equal to ah, which means k equal to minus 1 over tau. That's what you see in the literature. But do not get confused. Suppose if you calculate k equal to 1 over tau, this becomes a 2-factor. That means all the super horizon power spectrum is just a factor of 2 times times when you evaluate at horizon exit. So this is just a rescaling factor. That's why people take it as a horizon exit. And also another reason is once the mode exit horizon, it quickly becomes classical, almost in very much less than 1 e-fold. I did not spoke about e-fold so far, right? Well, e-fold is basically how much universe expanded during inflationary regime. It is measured by logarithm of a. Well, a by a naught. Basically, let's say inflation starts somewhere, it ends. So that's the duration. Is basically measured in terms of logarithm of a by a naught. You see, an expansion of universe is decided by the clock. That is the scale factor. Tells you how much e-folding time happened. Well, curiously, this e-folds language used by Meissner in his article Absolute Zero of Time. That was the first time I saw, but maybe people used it before, I don't know. But it's inspiring to read a lot of all the developments we see today kind of link to this article. The amazing thing about this article is that it has no single equation. It's all physics explanation. That's again art. It's very difficult. How do you explain things without writing equation? You see, you have to write a lot of things to understand. Yeah, anyway. So we will come back to that e-folding picture later. So this is the power spectrum, but story is not over yet. So normally, to compare with observations, you need a fully gauge invariant variable. And that variable is called the curvature perturbation. Yeah. As scale factor grows, well, tau goes to 0. So in the infinite past, tau is so big that physically mean that the particle horizon is very, very big. All the scales are inside the horizon or in causal contact. So as inflation proceeds, scales exit the horizon, and then tau goes to zero, but it does not exactly go to zero, because at the end, at some point, inflation ends.
Yeah.
Yeah.
Your how approximately the measure of the end of the inflation?
Yeah, but not precisely, but it's like infinite future. But the point is, let me explain you this. You see, you look at the power spectrum. In the limit tau goes to zero, it just approaches to a constant. Okay, that means your power spectrum, the amplitude is frozen on super horizon scales. That means it never changes in the future evolution of the universe. Then that's what you measure. That's what you can relate to observations. Yeah. Yeah, but k going to zero is nothing but this super horizon limit, this one. So you can either say this way or tau going to zero. Actually, this way is better. Thanks. So we should tell this way.
Wavelength will be larger than the average.
Yeah.
Than the
Particle horizon. The exit. Yeah. Once exit, become classical. Because it is classical, then you get an amplitude which is almost approximately constant. Does that mean that quantum nature gone? Let's come back to that. Okay. So then also, but we evaluate actually in relation to observations. So for another, the actual gauge invariant variable, delta R by R dot psi. Well, the way you understand it, basically, see, it gives you an equation of motion, right? This R plus R square action. Whatever coming from R square, you write it in the right hand side and treat it as a energy momentum tensor, but still in the Jordan frame. And then you look at well, gauge symmetries, the diffeomorphism invariance, and define a variable that does not change under any transformations. And this is a useful quantity. And if you compute this, psi plus psi delta R by R dot, remember, R is 12h square plus 6h dot. R dot is 24h dot. And this one is negligible, h double dot, because it's not varying much. You can write it as minus 2 R bar h epsilon. Epsilon is minus h dot by h square. There should be a h somewhere here. Sorry, do not remember this. H by R dot. So yeah, this should be, it's not psi, it's h. And delta R, you remember we got a constraint equation. Sorry. If you plug in everything here and in the approximation, because this is epsilon is huge and it comes in the denominator, this is called the curvature perturbation, and this is approximately equal to minus 1 by epsilon psi. So ultimately, the power spectrum, the correlations you measure that related to observations is the correlations of this curvature perturbation, which is a fully gauge invariant quantity. And we already computed power spectrum for psi. If you want power spectrum for R, you just divide by epsilon square. Because power spectrum is 2-point correlation, so curvature perturbation is 1 over epsilon times psi. Psi square is 1 over epsilons. Sorry, R square is 1 over epsilon square, psi square. And well, I should not write it here, right? As a separate expression, the final result. Where is it? Okay. So afterwards, we will derive everything in the so-called Einstein frame, but that derivation will be super fast because all the details exist in the literature. This one exists in only very few places, and in some places with a lot of mistakes, incorrect expressions. So uh, I will mention in the lecture notes in which articles it is mentioned, where are the mistakes, so that you clearly know and you can check yourself the calculation. Ultimately, you have to believe yourself. Do not trust any calculation, even mine. Okay. Power spectrum is 16 pi square, 1 over 3 f0 r bar h square 1 over epsilon square. So in this derivation, I already absorbed that factor of 2 evaluate. This is evaluated k equal to ah. Okay. So there are minor details of factors of half and things. I will explain that in the lecture notes, but this is the final result. You can cross check. Okay, cool. And you can repeat the same procedure for the tensor fluctuations. Tensor fluctuations are basically defined by d tau square plus 1 plus 2 hij delta xi delta xj. Because this same expanding background generates gravitational waves. In fact, whenever you have source, you always generate gravitational waves in most of the situations. Well, although there are some alternative frameworks of inflation, which say like there cannot be any gravitational waves, but that is a bit strange because you need very complicated physics to stop gravitons to propagate. So epsilon is the so-called slow roll parameter. It is minus h dot by h square. Well, let me write this relation. So remember that solutions we worked out, if you compute epsilon in the so-called number of e-folds, and normally we count the e-folds from the end to the beginning of inflation, in the reverse direction. There is a reason to that. If you want to, I mean, from the CMB and everything, what is needed is some specific number of e-folds. Let's say it's not about needed. Whatever that affects the CMB is only those fluctuations generated in the last 60 e-folds. There may be some expansion happening even before these 60 e-folds. That is irrelevant for the CMB. Okay, so you can still continue that to the past. Your de Sitter phase continues, and maybe there is no singularity, but that requires more understanding of quantum gravity. But what this tells you a message that quantum gravity doesn't need to start with always Minkowski. So there can be, you can have a situation with the Planck scale physics can be related to de Sitter. So this is how, like in the literature, for example, there is a very nice paper by Edward Witten, Quantum Gravity in de Sitter space. It's a huge, very interesting topic from a lot of directions of quantum gravity research, and a lot of progress and questions remained, and from the context of string theory, which you all knows very well. I don't know, did you mention de Sitter? No. Yeah. Okay. Yeah. Sorry for asking, but I was doing some little calculations of this sometime. I forgot. Sorry, but yeah. Anyway, this you heard from Ivan and Ivano. Sorry. Yeah. Okay. Now you do these perturbations and compute tensor power spectrum, but then you do another step here because you have two polarization states. Luca has derived the propagator tensor field has two polarization states. That means whatever you get, you multiply by a factor of 2. Okay, because you have two polarizations. So you compute the tensor power spectrum in the similar way. You get similar equations, which I'll skip, but the details are in the notes. So the end result is something like after you multiply this factor of 2, 1 over pi square f0 r bar h square. That's it. This is what you get, tensor power spectrum. And then this is the observable. Luca mentioned at the end of this talk, the ratio of tensor to scalar power spectrum. And it is expected to be much less than 1 because the the scalar field is the dominant field during inflation. So it produces more fluctuations than the tensor. And that's why in the CMB, you have this. In the CMB fluctuations, most of it is generated by the scalars. And there is a tensor component, but then it is in the so-called B modes, which are still to be measured. But if you compute this, you get 48 epsilon square. But still you do not have a number yet, right? Let's get to that number. This number comes from, we got the solution. Yeah,
Yeah. And so the spectrum does not depend on H, right? Does not depend.
it does.
It does not have.
PT does not have. Well, epsilon will enter. You have to go to the next order in perturbation theory, but that is, I mean, power spectrum is mainly given by a constant term, but there is something called tilt, which comes from the next order correction. So, I mean, if you do not see something epsilon there, is just there is a small correction. Yeah, zeroth order.
Scalar power spectrum. Yeah,
At the zeroth order, 1 over epsilon square. This is exactly says you that scalar power spectrum is huge compared to tensor power spectrum. Yes. This is general feature of inflation. Yeah. If you have the quasi-de Sitter background, which is often called the slow roll, well, the precise definition of inflation is quasi-de Sitter. Okay. Slow roll is a definition used by scalar field models of inflation with which is a bit more involved, let's say. If you say inflation, it is quasi-de Sitter. That's a more precise definition. That's a definition exactly used by Starobinsky. And this is PT by PR. It's called tensor to scalar ratio. And if you compute epsilon from here in terms of so-called E-folds, because you have the scalar scale factor and everything, and you get 1 over 2n, well, approximately. Okay. And n is very large because you want inflation to last for some time. And this gives you, yeah, 48, yes, some 12 by n square. This is the prediction of Starobinsky model, which gives you, well, for n equal to 60, R is 0.003 something. And the current constraint from on the primordial gravitational wave, this is exactly this tensor power spectrum is exactly called the primordial gravitational wave. And that constraint on the primordial gravitational wave is 0.036. Very close. So that is, in the next decade, we will see what's the prediction of this theory. But this theory has more of other features, which we will see in a while. So in principle, after the Planck 2013 data, so that's where when I started my PhD. So exactly, I joined as a student and the data came. And my supervisor said, no, this is a huge data. Look at it, look at it. Well, I don't know what is inflation. So anyway, but you see, in these few years, there's a lot of progress has been happened. In 2013, the constraint was 0.1, and now it came down to 0.036. So Starobinsky in 1979 first came up with the idea of a de Sitter phase, and he derived for the first time primordial gravitational waves. The existence of primordial gravitational waves is the first derivation. Then later, he came up with a theory and a precise prediction. So this derivation has pushed the boundaries, technology, and everything to reach this much precision. So it's important for theoretical physicists to get a prediction without free parameters so that we push in all way the human progress. Well, this sounds a bit philosophical, but it's true, right? But anyway, uh, any questions so far? Yeah,
Sorry. What's your power spectrum? The A equal AH.
yeah,
Is the horizon axis.
horizon exit.
Okay. And like the calculation for when you solve the Cantor-Sartor equation.
Yeah,
Was valid like in for K much smaller than
no,
AH.
no. K, it's not about validity. See, we have a lot of choice of vacuum. To choose a vacuum, we look at in this limit, in the subhorizon limit, we want the quantum field to behave like in Minkowski. That is, once we fix that, then we get the quantum field description in the entire de Sitter space. Yeah,
My understanding.
Yeah.
Usually in inflationary model, there are like the spectral index.
Yeah.
And,
I haven't derived that. I will have to speak about it. Yeah.
Even if you fix the spectral index, the number of e-folds is still a free parameter in principle, right?
Num-
Starobinsky validated, so it means that if you measure spectral index, n will also be more or less fixed, right? Because we have one minus, which is I think something important as compared to the inflation, because you have less free parameters.
Yeah, you have only single parameter. So the number of e-folds, if you fixing number of e-folds already fixes the scale. So or the other way around, there is another yeah, basically okay, let's put it this way, right? So epsilon well, I need to derive another one, sorry, another observable, which is spectral index. Let me derive that and then I answer your question. So okay, I hope this is clear. Let's keep this and erase these parts. Okay. So we get the power spectrum PR to be this expression, which is proportional to 1 over epsilon square. Okay. But you see that power spectrum is function of K, right? Function of momenta. Where is the function of K here? Any idea? Power spectrum by definition is something K cubed by 2 pi square modulus of this square. Well, this is curvature perturbation, so this is basically the definition of power spectrum, which is just a Fourier transform of 2-point correlation in the position space. And then you derive everything and you accept this formula. Great, excellent. But where is the K dependence? Excellent. Yes, that's the right answer. But can you explain more? Yeah, okay, excellent. You got it. Anyway, let me repeat what he explained to me. So that you evaluate this power spectrum at K equal to AH. So this is the power spectrum for each K when it exits the horizon. And you look at logarithm of K, logarithm of A, as logarithm of H. And normally you evaluate, you count number of e-folds from end to the beginning. So that means you write it with n. Okay, then you write dln k is minus dn. Now you can compute the so-called tilt, how that tells you how the power spectrum depending on k, and this is related to d ln p, d ln k, but just use that. So it is 1 over pr d ln, well, dp by dn and substitute or favorite epsilon 1 over 2n, and you get minus 2 by n, and ns is 1 minus 2 by n. So observations tell you the tilt, that is for if you plug in n equal to 60, ns is 0.964 something. There is a constraint, something of that kind, and this observation tells you, because this is related to the scale invariance, how much scale invariance is there in the CMB, and that tells you 60 number of e-folds. And once you know 60 number of e-folds, you have epsilon, which is 1 over 2n. But if you go back to those formulas, it is m square by 6h square. So you can determine, if number of e-folds is given, you can determine epsilon, and indeed that's what gives you this tensor to scalar ratio. And then there is still something is left, this number m. What is its value? You get a relation between m and h here, but you don't know the value of m. So Planck data has measured, well, it's not only Planck, I think the one WMAP has already measured this ns minus 1. So this amplitude is related to, it's about 10 power of minus 9. Okay, let's more precise, 2.2 times 10 power of minus 9. And this gives you the value of scalar on mass to be 10 power of minus 5 Planck mass, 1.3 times 10 power of minus 5. And H inflation is 5.5 times 10 power of minus 5. Then you see the inflationary condition is R much greater than 3m square. If you plug in this number, R is 12h square nearly during inflation. And you plug in these numbers, indeed, R Ricci scalar is more than 10 orders of magnitude than m square.
Each inflation will be evaluated in x.
During inflation, H is almost constant for all the 60 folds. And in the last less than 1 fold, it jumps down to the smaller values. So it's for every mode that exists the horizon, its H is nearly the same. Well, it is nearly exactly explains you why your spectral index is not exactly 1. It is close to 1. So, and ns minus 1 is, if you compute it, it is 0.04 something, and minus 0.04. That's why it's red tilt. So your power spectrum decreases slightly as k increases. This is related to the CMB multipole curve. I will explain that once I switch on the, I don't know what it is, but yeah. Projectors, yeah.
The condition is R, so h squared is much larger than n squared, factor of order 1, but they are both 10 to the minus 5.
No, 6.
Oh, it's a 6.
Oh, no. Sorry, this is 5.
They are both, but they are basically the same one.
Well, you have 5 factor here, and you write it, you square it, you get 25, and you multiply with 12h square, you get huge.
So it's 2 orders.
Yeah, it's 2 orders of magnitude. Good question. So I will come back to that. So AS is
2.2 times 10 to the minus 9, right?
you're asking this. Okay, I was thinking a very deeper question. Okay. Sorry. Yeah, it's 2.2 times. Let me write it precisely. How much time I have? Okay. Thanks. So yeah, But there is a lot going on there. There are some things needs to be explained, but I did not explain you what are these scales and what is K, and so what is it, how is it related to CMB? What all this about? Yeah. Yes, reduced Planck mass. Yeah. What all these things? Let's try to understand in the next 10 minutes a little bit about observations. Okay. Can erase this piece. We don't need solutions once we get the final answer. But we need physics. We should keep this. Okay. So what is CMB? CMB is temperature fluctuations delta T by T0. T0 is the temperature of the CMB, which is 2.7 Kelvin. It's a perfect black body spectrum measured by so many probes. Now, this is, you look at the sky, and there is a surface of large scattering, and you measure temperature, that you measure CMB photons. You collect them from all these telescopes, satellites, whatever you call, Planck satellite and WMAP. So many years it has run. What you measure is temperature correlations, but you write in terms of spherical harmonics. And you compute correlations delta T by T0, E0, N1, N2, and this gives you W of theta. Theta is nothing but N1 minus N2. So you look at correlations at all degrees. And just substitute spherical harmonics, you get W of theta to be, I should look at notes. You get Legendre polynomials from CL. I will define what CL is. 2L plus 1. CL is called the angular power spectra. It is 1 over 2L plus 1 summation over M A LM square. You have to do summation over M because it is a angular power spectrum. It just depends on L. So you do it in spherical harmonics, right? So CMB large scattering, we are at a distance from the CMB, the surface of large scattering, and this distance is measured in a scale, some K, let me call it as KS, and it is measured in some distance. It's notationally written like this: the distance from us to the surface of large scattering, and this is about 7 into 10 power of minus 5 megaparsec inverse. That means it just tells you that you have some size. That's what you can observe, nothing else. Yeah. T N is just the direction. So you in this direction you calculate, you see the CMB photons, and this direction you see the CMB photons. What? Yeah, angle is basically theta, that N1 minus N2. You look at this direction. Yeah, it's direction. Yeah. Okay. I have 5 minutes. I think 5 minutes enough, maybe. Okay. This is what it is, and you may wonder why it is defined CL to be 1 over 2L plus 1. What is ALM? ALM are the Fourier coefficients of the temperature fluctuations. You write in spherical harmonics. And CL is the angular power spectrum, is just sum over m, okay? But what m runs from? N runs from minus L to L plus 1 values for each L, and you divide that 2L plus 1. Basically, it's kind of averaging. For each L, you have m number of points, and you measure that, and you take a summation of all squares and divide by how many number of points you measure. Okay, this already tells you for if L is small, you have only few data points. If L is large, you have more data points. And there is a relation between theta and L, which is approximately 180 degrees by L. And in the CMB, we always start with L equal to 2. L equal to 1 is excluded. There is a very fascinating reason for that. So our Earth is moving, right? So surely moving around in the solar system. It's moving. Well, Earth revolution is around 30 kilometers per second, roughly. I think, yeah, just from my childhood memory. So, because of the Earth's motion, the CMB looks like a dipole. So you see hot and huge cold spot, but this is created by our motion. So basically you get it's related to double shifts and so you get this you look like a dipole. Then you say that look, we are observers moving all the way from the Big Bang to here, although we don't literally exist at the Big Bang, but anyway, just imagine that imaginary observer. Okay, so the co-moving along with the expansion of the universe. So that means the universe should look statistically homogeneous and isotropic. So then you measure Earth's motion with respect to the CMB. Okay, and that is around 348 kilometers per second per megaparsec. Okay, okay, I will write in the notes. But it's some number. Okay, you get that number because you want to remove the dipole, and then you infer that that must be our velocity with respect to the same b. If you remove the dipole, then we place ourselves as co-moving observers. This is again a very open challenge to a lot of observational people. Is it true and all? This is active area of observational research, but let me not go to that. So there is a lot of H0 tension and everything. They think that maybe our motion is so peculiar or not. There are some tensions, but CMB, as far as CMB is concerned, and it is perfectly fine. You remove the dipole and you start with L equal to 2. That tells you that you start with angles 180 degrees and less. Well, let me give you fascinating things. We have basically several probes, Planck and WMAP, all these data. So do not think that the old data is bad and new data is great. You should never think that. And it's also true for research papers too. Old research, it's done, we have advanced so much. No, that assumption is not correct because history of science teaches otherwise. Okay, especially in the data, there are several things. If you take WMAP data, WMAP is a satellite which measured the CMB temperature. It has measured in a different way. It has like a two kind of cameras, so it always looked at 2-point correlations here and 180 degrees here and joined them. It's like always take 2 points and take an average. But Planck is a telescope which is kind of rotated it and collected the CMB photons. So there are some advantages and disadvantages both the methods, and there are some issues which we still do not understand in the CMB, and which I will discuss briefly, maybe 5-10 minutes after the coffee break. But let me finish it 1 minute, please. Okay. So CL, after all the computation, 2 by 9 pi times dk by k power spectrum of curvature perturbation, and some Ks I defined here. Some K by Ks. Okay, from where this is come from, this is the Bessel functions. And well, this is coming from basically, you see the CMB photons traveling from the surface of Lord scattering to us. So some standard calculation gives you these Bessel functions. And this is the power spectrum you calculate from your theoretical model. And that's how you get the theoretical CL. Observations, people do not need this formula. Observational people directly observe this. Why do they need this? This is a tool for us to check our theory. Okay? Now, all this is done, and this is known from ages, okay? And people already expected power spectrum to be AS, K by KS, K star related to NS minus 1. This is an ansatz, and NS has to be close to 1. This is called the Harrison-Zeldovich power spectrum, which we started in the beginning of lecture yesterday. Okay, but here we gave a clear theoretical reason why you should expect this, and this is the fundamental foundational reason, and we do match with this quite very well the expectation. That's the end of the story more or less, but let me also tell you one minor piece. If you look at the CMB plots, what you see is a multipole curve. So you have L into L plus 1 divided by 2 pi CL. Well, you kind of do a bit more radius. Can you see it? No. Perfect. So then you have this multipole curve with some oscillations. So these oscillations describe you energy content of the universe, that is your matter, dark matter, which is clumping, which is causing the clumping of the structures, and you have radiation and photons, which always try to escape. Then matter squeeze in, so there is a damped oscillation. So there's a gravitation, compression, decompression, compression, decompression of all stuff in the universe, and that's what creating these acoustic oscillations. And so you add to these CLs additional elements, a new element which is related to the parameters of lambda CDM, some classical physics, fully classical physics. Okay, some elements, let's say you add a lambda, which is a constant, and the CDM, which is basically the cold dark matter, and this tells you why this happening, and lambda tells you where the peaks are. If the lambda value is different, the peaks will be shifted. So it's so precise data. If you are thinking about dark energy, you want to make your own model of dark energy, not cosmological constant. You have to be careful with this. You have to be careful with this. So if you do this, then your multipole curve shifted, but this is precisely measured. And this peak is exactly correspond to the so-called pivot scale, 0.05 megaparsec inverse. I mean, do not get confused, this megaparsec scale, let's say our size of the galaxy is of the order of kiloparsec. Megaparsec is whole entire universe, okay? Now, this scale corresponds to the angular correlations about 1 degree. And this is exactly the inflationary prediction matches, and we have huge success with the data. I think I will end this for the coffee. Thank you very much.